Hi there, Mrs. Thompson here, and today we're going to talk about molecular geometry, which is just the shape of molecules. So far in class, we've been drawing molecules in 2 dimensions. We've been drawing Lewis structures, which is great to see what's going on with the electrons and which atoms are forming single bonds and double bonds and even triple bonds. But it doesn't tell us what the molecules actually look like in 3 dimensions in real life. So the chlorine around the carbon atoms are actually spreading apart more than what you see on a flat piece of paper, more than what you can put on 2 dimensions. And so that brings us to something called VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory. Okay, instead of saying valence shell electron pair repulsion theory every single time, we shorten it. And to make it so that it rolls off the tongue, we say VSEPR. We don't actually say VSEPR, which is how you would sound it out. We say VSEPR. Okay, so what is VSEPR? Well, one thing we have to know is that electrons are going to try to repel each other because they are like charges. They're going to push each other away. And so in a molecule, you have electrons all around the atoms, and those are repelling each other. And so the atoms that are on the outside are going to push each other away as far as possible. And that's VSEPR. So what we're going to do is we're going to take a Lewis structure and change it into a VSEPR shape. So here are the steps. One is you need the chart that you have to memorize, which is this VSEPR table right here. Okay, if you don't have that one, then maybe you have this one. Okay. All right, so draw the Lewis structure. Count the number of electron clouds around the central atom. Okay, the way this works is a cloud counts as a single bond, or even a double bond, or triple bond, or a pair of electrons. Those all count as one cloud. And then we'll use the chart to determine the shape. We'll do that by looking at how many bonding and how many non-bonding pairs we have around that central atom. Okay, so let's do that with this one. We're just going to count the bonding pairs and the lone pairs. And so a bonding pair would be these lines between the central atom and the outside atom. So in total, it has 1, 2 bonding pairs. Okay. And then it has these electrons on top, which we call lone pairs because they're not bonded between atoms. They're alone. So we call them lone pairs. And so this molecule of water has 2 bonding pair and 2 lone pair. Altogether, we say it has a total of 4 electron clouds. So I'll write that, 4 electron clouds. Okay, so one thing we need to note, and I'll show you some examples with that in a moment, is that if you have lone pairs, because lone pairs are so negative, they are better pushers. They push bonding pairs away from each other. So we'll write that. It says lone pairs create a larger region of negative charge than bonding pairs and thus push adjacently bonded atoms even farther away from each other than normal. Okay, we're going to go through all of the shapes really quickly. So you need your VSEPR table handy. Okay, so I just want you to understand why they are the way that they are. You do not have to draw these as we'll be drawing other molecules later, and you do have that table. So here we go. We've got 2 bonding pairs and 0 lone pairs. And the only possible shape when you have this is a line. And so between the bond angles from here, between this bond and this bond, makes sense that this would be 180 degrees. Okay, next one is trigonal planar. This is when you have the next one on here, which was 3 total clouds, 3 of them bonding, 0 of them lone pairs. And so they spread out to get as far away as possible. And what you end up with is just this flat molecule. As you see this one kind of spinning around here, it all would be on one plane. And what I mean by that is it would fit on a piece of paper. So if I had the balloons that you're seeing there, they would all go flat on the paper. Okay? And so the bond angles here, it's like you take a circle and cut it into 3 equal pieces. 360 divided by 3 gives me 120 degrees. So each angle here between each bond is 120 degrees. We call this trigonal planar because this is our triangle here, and it's all on one plane. It fits on a piece of paper. Okay, this one is tetrahedral. It's tetrahedral because it has 4 angles. All of them are equal, 109.5 degrees. And so this is that shape here. It isn't just a cross like this, it's actually a little different. Okay, so what we have to notice from this one, and if you notice, this is the only one where you, on our chart anyways, that you start to see lone pairs. And so what happens with the lone pairs is the lone pairs are better at pushing than bonding pairs. And so here's our normal tetrahedral shape. We can change this by giving an example where you have a lone pair, like NH3. What's going on here is the lone pair is actually pushing harder than that bonding pair on the hydrogen would. And so the bond angles are kind of more squished together. So these are, excuse me, where am I? These are squished closer together than these would be. Where these are 109.5, okay, this lone pair pushing down further makes these 107 degrees. And so it would look something like this. Okay, next one is when you have 2 sets of lone pairs, 4 electron clouds in total, 2 of them lone, 2 of them bonding pairs. And so you end up with this shape. The lone pairs are pushing them closer together, these 2 lone pairs, than they did over here. So it would be 104.5. And this is what it would look like. Okay, this one is trigonal bipyramidal. It's trigonal bipyramidal because you have basically a trigonal planar shape right here. So you notice when this turns around right there, that flat part is a trigonal planar shape. And then you have one above it and one below, which makes a pyramid here to here to here. And then on the bottom, it makes another pyramid. So that's the 2 pyramid part in trigonal bipyramidal. The bond angles here are 90 degrees in this part. And then the part where it goes in like a triangle, that's 120 degrees, just like the trigonal planar. Okay, here you have the octahedral geometry. This is when you have 6 bonding pairs and 0 lone pairs. In this one, you can see there's 4 this way, and then as it turns around, you can see from those 4 in that flat plane this way, there would be 1 above and 1 below. All of them are 90-degree bond angles. It's kind of like looking at a jack. Okay, when we draw VSEPR shapes, and I do want you to draw this one, you need to be able to tell what's going on with the different line representations. So, here we go. First one, when it's just a single line like this, that means it's in the same plane as the paper. Okay, so here's what I mean. I tried to make a molecule. That's some toothpicks. Okay, so the same plane of the paper. So that means if I look at my molecule here, these 2 are right there. If I cut the molecule, it would rest on the paper. This top one right here, and this one right over here. So those are resting on the plane of the paper. Okay. Then you have this one, which is going behind the plane of the paper. So in my molecule, that would be behind the paper, what would cut through the paper. Okay. And then this triangle is actually what's coming in front of the paper. So here those two are in the line of the paper. This one's coming out in front. Gosh, I can't do this very well. So right there, out in front of the paper and then behind the paper. So that one's in front. Right, so here's our first example. What we're going to do is take a look at a Lewis structure that's already been drawn. That's for CO2. And we're going to count the number of bonding pairs and lone pairs and then use our VSEPR table to figure out which shape it is and name it. Okay, so here we go. I've taken the time to draw this out. I counted the valence electrons. I've arranged them in order to get octets. Okay, then I count. This is 2 bonding pairs around the central atom. Okay. Even though they're double bonds, they only count as 1 bonding pair. There are no lone pairs on the central, so that's 0 lone pairs. And so if I look at this chart, I have that shape. That's 2 clouds in total, 2 of them bonding, 0 lone. Okay, and so I'm just going to draw it exactly like that, except for I'm going to replace the E and the X with the actual atoms that are in the Lewis structure. So it looked like this. Okay. The other thing you have to do is write down the angles. And so I'm going to label that as 180 degrees. So 180. And it's also linear. That's the name of the shape. So draw it, write the bond angles, and name the shape. Okay, example 2 is boron tetrafluoride. Remember that this has to be drawn using Lewis structure steps. It is electron deficient. That's why you don't see an octet on the boron. Okay, so what we're going to do is count the bonding pairs and lone pairs. So 3 bonding pairs around B and 0 lone pairs around boron. Okay, then we're going to look at our table. And so 3 total electron clouds, 3 of them bonding and 0 of them lone pair, is trigonal planar. And so I'm going to take that, I'm looking at my chart, I'm going to take that and I'm going to turn that into B and S. So boron in the middle, fluorine on the outside. Then I'm going to label the bond angles. So that's right here to here. That's 120 degrees. And I'm also going to name the shape trigonal planar. Number 3, we're going to do the shape for water. And so we've got 2 bonding pairs, 1, 2, BP for short, 2 lone pairs, 1, 2, LP for short. And then we're going to draw the shape. I'm going to draw it exactly how it is on here, except we are replacing the E's and the X's. Okay, so O in the middle, and then there's a line above, which means it's on the plane of the paper, a line to the side, still on the plane of the paper. Then there's a dashed line going back, that's behind the paper, and a triangle coming forward, that's coming in front of the paper. And then the X's are at the bottom, so I'm going to draw my hydrogens down there and my lone pairs on the top. Okay, then I'm going to label the the bond angles, which is 104.5 degrees. And this is called bent. Last example. Okay, phosphorus pentachloride. Counting the bonding pairs, 5 bonding, 0 lone. Okay, looking at my chart, I see that 5 total electron clouds, 5 bonding, 0 lone, is trigonal bipyramidal. And so we're going to draw it exactly like that, this one right here. Okay, so I'll put the phosphorus in the middle. Then there's 3 lines. Then there's 1 line that's dashed going behind the plane, 1 coming forward. Put the chlorines all around. And then we need to label the bond angles. Well, there are 2. It says 90 and 120. So 90 happens right there. And the 120 happens on this part. It's the trigonal planar part. Never mind. And it's between those 2 chlorines. Okay, actually it is also here and then between this one and that chlorine. Okay, and then the name of the shape is trigonal bipyramidal. Okay, so we'll be doing these in class tomorrow. It's a matter of you getting to know this chart, using it for a while, and then memorizing the chart. These are the only ones that you have to memorize. There are more out there, but these are it. Okay, come to class with questions. I know you have them. This is highly conceptual. So I will see you soon.